Well, in another riveting fireside chat, we're looking at acids and bases. If we were to do some nomenclature practice and go through and look at these, we might refer to that first one as dihydrogen sulfide. We have dihydrogen sulfate, so note the name change. And then in that last one, it all of a sudden becomes sulfuric acid. And we get this big shift. Why do we get this big shift in the name? Okay, well, that big shift in the name comes from the fact that we have hydrogen in front in the AQ, which meant an acid. Well, why do I care? Why do I need a different name for an acid? It gets a different name as an acid because it's one of the kind of core or first discovered reactive things. Okay, so observationalists, which is where a lot of science starts, or all science starts, is with an observation. And they noted that certain compounds had some interesting properties. So believe it or not, they would taste these compounds and they noticed that they had this sour taste to them. And it also, on their fingers, made it feel kind of sticky. And so they were great. They had these characteristics. They also potentially tested these to realize that that sticky feeling was their hand dissolving. The sour taste usually resulted in death. Like, there were all sorts of kind of bad side effects. But they went through and they came up with a description behind these things. Okay, and that word that they used to describe these was acids. Okay, and they, from the root, I believe, acre or ACR, which is like kind of bad tasting, maybe something like that, sharp tasting, and that's where we're getting acids from. Well, as observationalists continued to note substances, they also found these other substances that were bitter tasting and kind of slippery feeling, and perhaps by chance they ended up mixing these things, and in the process of mixing them, they got a awfully hot reaction. And hot, while spelled with an H, is not followed by 2O. They got a hot reaction. So that hot reaction then added a potential hazard with this. So they wanted to make sure that they could go through and ensure a way to name these things such that we would know to keep them separate. Because if they accidentally mixed, we would get this very hot, boiling, dangerous system. So they labeled one as acids and the other as bases. And what they found was the things that they labeled as bases all had this bitter taste, slippery feeling, and those that were acids had this sour taste and sticky feeling. What we have later come to learn is that what has happened when they were mixed was what is a neutralization reaction. And in that neutralization, we know from earlier in the semester that it forms salt, and here's where that H2O is coming from, and water. And we've now neutralized the activity of those materials. But that's kind of our origin here. And so what we get are acids and bases. And so what we see below is a standard acid, and the patterns that we found earlier on for nomenclature is that we typically saw an H in front and we usually see an AQ in back. That is a vastly oversimplified definition, and you'll note that this particular instructor typically hates showing phases and has unintentionally removed them from each of these things. Okay, so that could make it a little bit more challenging to deal with. Our bases, we know to be bases because they reacted with the acids in this neutralization. Well, that in and of itself as a definition is a pretty piss poor one, because that means the only way that I know that I have a dangerous potential reaction is to react it and thereby see that it was dangerous. That's a bad system. You end up exposing yourself to those dangers in the process of that discovery. So what we would like to do is come up with some way that we could define these things. And that first definition of acids and bases, that now is a little bit broader than H in front and AQ in back, came out with the Arrhenius Definition. And so in his definition, what he went through and said was that if we take a substance, namely an acid, and we add it to water, what happens? If the hydrogen ion concentration goes up, we would then reference the HCl species that we started with as an acid. And that's it. Okay. So what if it was HC2H3O2? Well, if I add it to water and I notice the H plus concentration goes up, then, well, it's an acid. So I'm doing a relatively simple reaction because all I'm doing is really diluting it with H2O, with water. So it's not a big deal, and we can make these conclusions. What happens with our bases? Well, Arrhenius went through and noted with the bases that he was picking up or using that if he did the same thing and added them to water, and we saw an increase in hydroxide ion, that was labeled as a base. And before we start going, well, why would we pick these arbitrarily or seemingly arbitrarily identified things as H plus and OH minus? Why did we pick those ions to characterize our acids and our bases? It might be helpful to remember that when we mixed these, we got a neutralization reaction, and in that neutralization, we produced the substance of a salt and H2O. Because you're in theory listening to this lecture because you've liked how I've presented things, or you've been forced to, you may have also seen that we could have written H2O as HOH. And why is that important? Well, where did the H come from? The acid, the OH from the base. So really, Arrhenius' definition was acknowledging that water was such an important substance, and that if we could split it into the pieces that are reactive, and they become reactive because they're trying to neutralize each other or neutralize their reactivity through the formation of water. Okay, so this is Arrhenius' definition. And I get a bit melodramatic here when I go through and call this useless. It isn't that it's useless. Okay, it is very useful, and we tend to use it, I would argue, probably through all of general chemistry, because those reactions all run in water environments. And as long as we're running in water environments, this definition works out phenomenally well. Okay, so that is our first definition, is our Arrhenius definition. Acids increase hydrogen, bases increase hydroxide. The second definition to come along was Bronsted-Lowry. Why create a new definition? Well, we noted that there were certain circumstances that we didn't see the presence of hydroxide, but they were still neutralizing our acids. So we're still getting this neutralization happening, but we aren't seeing it through the process of water, which means we need to tweak our definition to expand the reactive labeling to a larger system or a larger environment. Okay, and that's where we get our Bronsted-Lowry definition. And the Bronsted-Lowry definition decided to really still keep the hydrogen ion donor aspect. So our acids are still going to supply H+. And really the base definition is now different, because the base doesn't say that it has to be hydroxide. It can really be any species. The base can be anything as long as, through the course of it acting as a base, it accepts a hydrogen. So it must somehow accept a hydrogen. In the process of accepting H+, it becomes positively charged. This is now our hydrogen ion acceptor, or our Bronsted-Lowry base definition. Okay? This increases the breadth or the range for our acid-base definitions, so it can now apply to a larger range of reactions, which is pretty cool. Okay? To that end, when we talk about acids and bases, and actually not to that end, it applies to a broader range. But the deal with applying to a broader range is that it must still also apply to our old definitions of Arrhenius. Well, the acid one still makes sense. We're still seeing hydrogen. The base one becomes a little bit more confusing. How is the base one still incorporating both Arrhenius' definition and the Bronsted-Lowry? Well, if in the course of acting as a base, we would accept that hydrogen, we've now satisfied the definition. Hydroxide does accept hydrogen to neutralize the acid. So hydroxide still fits within the definition. It is a hydrogen ion acceptor, or it can accept hydrogens. So it still fits. Really what the Bronsted-Lowry definition says is that other things other than hydroxide could also accept electrons and still be defined as a base, without having to center on the the water aspect of our acid-base definition addressed through Arrhenius. When we think about our acid-base reactions, there is a third. That third definition is the Lewis definition, which now changes focus entirely and only looks at the electrons. That is much more difficult for students to process because when we look at a chemical reaction, we don't see electrons move around, we see atoms. And that's why we don't have a slide defining those Lewis definitions, because it's not necessary at this stage in the game except to know that there is a third option, and it is called the Lewis definition of acids and bases. Where does this ultimately then go is being able to apply and see what we can come up with. So we've got two reactions set up here. Okay, the bottom one I'm going to leave you to go through and solve. The top one we will work out together. So let's go ahead and take a look at the top one. We've got two species and we've got to decide whether they are acids or bases. Okay, to help out, our acid we said was a proton donor. Okay, why do we call it a proton? Well, what it's donating is H+. And if we go back to our definitions of subatomic particles and we were to build a hydrogen ion, well, it has no electrons, it has no neutron because it's hydrogen, all it has is a single proton. So H+ is effectively just a proton. Okay, so what we would need to look for an acid would be something that has hydrogen in it. This is why we're starting with this one. H3O+ is the only one that has hydrogen in it, so it's going to be the acid. What is our base? Well, the base must be a proton acceptor. To accept that proton, okay, it has to have something to give to hydrogen to keep hydrogen connected. Well, since the hydrogen is positive, what that base needs to supply is some source of electrons. Electrons are negative. When we go back and look at our structure here, SO3 minus 2 is negative. It's going to be our base. How do we apply this to our chemical reaction? Okay, well, what am I going to do? I want to have that SO3 minus 2 act as a base. If it acts as a base, it must accept a proton, which means I need to add a hydrogen to the formula, HSO3. What happens to its charge? Okay, and at this point, all we're doing is doing one reaction here. What happens to its charge? Well, if I add a single H+ to that formula, I'm going to cancel one of those negative charges, and my overall charge will become a -1. Okay? Well, where did that hydrogen come from? Well, that hydrogen had to come from our acid. So what does an acid do? Well, an acid is a proton donor. So that means it loses H+ in the course of the reaction, which means I need to get rid of a hydrogen. So instead of being H3O, it'll be H2O. Okay, so I got rid of that hydrogen. What happens to its charge? Well, it started as a positive, but I got rid of H+. So I lost a positive. I'm now going to be neutral. I only lost one positive. So there it is. And there would be my chemical equation representing this whole process, which is kind of neat. Okay? And I'm going to draw that arrow back on in just a second here. Okay, so what can we do after this? Well, again, acids and bases, I want you to be able to address what species are acting as acids and bases. So let's go through and look at this reaction and look at a kind of new piece to it. That new piece you might see in between. What is special about that arrow that we're now using to represent this reaction? Well, there's two. It goes left to right and right to left. On the empty side of an arrowhead, so there's an arrowhead, we have reactants. On the pointy side of our arrowhead, we have products. Well, if we turn the arrow around and have it aim the other direction, the pointy side still points to products, and the other side would be reactants. This becomes a challenging concept because we are now flipping the reaction. Reactants aren't always on the left. Products aren't always on the right. They can be on either side depending on our point of view for an individual chemical reaction. So let's use that information to address our point of view. If we take a look at HSO3 minus, which species does it look most like on the product side? Okay, hopefully what you can acknowledge is that looks an awful lot like our base species, the SO3 minus 2. Well, for HSO3 minus to go to SO3 minus 2, what did it have to do? Well, it had to lose a hydrogen, or lose H+. That lose could be a confusing term because we've used that in oxidation and reduction. So instead, let's switch that to donate. Okay? If it is donating H+, that would mean HSO3 minus is acting as an acid. Okay? So interesting, our reaction now has two acids. Well, what happens for the other one? Okay, our H2O. It went to become H3O+. Well, how did it go through and do that? Well, to go from H2O to H3O+, it had to accept NH+, which thereby means that species acted as a base. So cool, we're now able to label acids and bases regardless of where they show up in a chemical expression as either reactants or products, and be able to interpret how those molecules could change their potential reactivities. That's kind of cool, and so that's what we're really trying to get at with this. But now how could we ask a question about this? Well, let's start it. Identify the acid. Okay, so a multiple choice question, identify the acid. Answer choice A, B, C, or D. And for those of you being like, well, it's B and C, you wrote acid underneath those. No. Okay? Only one answer is an acceptable answer. That makes things a little bit more challenging to be able to identify. Okay? And it addresses the issue with our labeling. We've called the acid and the base, and we've just said there's really no difference between reactants and products. But there is a difference. That's why we call one reactant and one product. This is where we introduce the idea of conjugate partners. Okay? On the product side, those aren't acids and bases. Those are conjugate acid and conjugate base. Okay? Conjugate meaning similar to. So the conjugate acid's partner would be SO3 minus 2. Okay? That's their relationship. So now when I ask the question, which one's an acid, you can tell me very cleanly it's H3O+. This clarifies our language and ensures that when we ask simple questions like which one's the acid, which one's the base, we know very specifically which one you're referring to. Okay, and so that's kind of cool. And so, whoa, that was not the button I wanted to push. Okay, what that now does is that cleans up our system, and we now have all of these phenomenal labels that we could go through and interpret. So what I would like you to go through and do, okay, is do the same process for the equation down here. HSO3 minus plus H2O goes to what? Predict what those products are, label out base, acid, conjugate base, put on your donate H+, don't accept H+, label the crap out of it like we've got up here. So again, I'm going to go ahead and say pause the video. That means click space or hit space, click the screen, click just the little pause button to stop the video, and solve that question out for me. Thank you. Good job for that. And here's your reward. And here's your reward for having done everything that I asked you to go through and do. HSO3 minus, because it is negatively charged, acts as a base and will accept a hydrogen to become H2SO3, making our conjugate acid. H2O, because it has hydrogen, will act as an acid and donate that hydrogen to our HSO3 minus to form hydroxide, and we now have our conjugate base. And we would have our lovely answer. But I said there was a reward, and I'm pretty sure that if you look at your work, you probably didn't draw what I just drew. Okay? which seems a bit odd. For those of you that didn't actually draw it out, you're like, well, I have no idea what's going on. I didn't draw anything. Well, maybe next time you should actually draw it out. And for those people that did draw a reaction out, they were like, but I didn't do that. Okay, I would bet that what you did was that one. What makes this interesting is that if we go through and we compare these two reactions, our HSO3 minus in one reaction acted as an acid, and in the other reaction, it acted as a base. Why can it do both of those things? Well, the definition of an acid was that it can donate a proton. Does it have a hydrogen to donate? Yes. So it makes sense for it to act as an acid, so the top one must be correct, which I'm going to bet is probably the one that you guys went through and wrote out. So why not write the bottom one? Well, let's look at the bottom one. What does the bottom one have? Well, the bottom one is HSO3 minus. Well, bases are negatively charged, so it should act as a base. So in this argument, who's correct? Well, we're both correct, okay? Assuming I didn't make any other mistakes within this, okay? HSO3 minus has the ability to act as both an acid and a base. That makes it amphoteric, okay? If we think about amphibians, okay, amphibians mean they can jump between both land and, not sea, water is the word. Amphoteric is following that same route. That amph root is saying that it can go both directions. It can act as both an acid and a base. Okay, and so that's what makes this interesting and kind of fun. At this point, what I now am going to have to kind of delay and shuffle because of video organization is that the next thing that we really want to address would be this double-headed arrow. That double-headed arrow I'm going to discuss in the next video on equilibrium. Okay, or not the double-headed, but the two arrow happening in there. Okay, that equilibrium is going to help explain what's going on in the next sequence of slides,